Suppose I went down to the store and I bought two 12-volt car batteries and I hooked them up to a single bulb like this. Now remember, the long line on a battery symbol is the positive terminal. So you see that these two batteries are fighting each other. This battery is trying to force conventional current clockwise, and this battery is trying to force conventional current counterclockwise. How bright is that bulb going to be? Well, it's going to be dark. Those two are equally strong, those batteries, and they're canceling each other out. So nothing flows through that bulb, and it's dark. Now I have a philosophical question for you. Is this in some way the same thing? I mean, if I just replace this battery, this 12-volt battery, with an open switch, the bulb is dark, just like that bulb, and I've got 12 volts, a 12-volt drop from here to here, just like I have from here to here. So in many ways, it's exactly the same. The only thing that's missing is the chemistry of this battery right here. We're using a gap instead of the chemistry to cause that 12-volt drop. Now suppose I go back to that store, and this time I don't have as much money. And so instead of buying two 12-volt batteries, I say, hey, just give me one 12-volt battery, and while you're at it, throw in a 0-volt battery. A 0-volt battery. Now, this battery is trying to force conventional current clockwise, and this battery is trying to make it go counterclockwise, but they're not pushing the same. Indeed, this one's not pushing. And so when I ask how bright is that bulb, well, it's very bright. It's 12 volts bright. Okay? Now, another philosophical question. Is this the same? I replace that 0-volt battery with just a wire. Well, we know from what we learned about circuits that for an ideal wire, there's 0 volts across it, just like this 0-volt battery. And so in both cases, I would have a bulb that's 12 volts bright, and in both cases, I would measure 0 volts from here to here. Okay? So in many ways, those are identical. Now, what does that have to do with a capacitor? Well, if I go back to this definition of capacitance, I see that I can rewrite this definition as the voltage across the capacitor is equal to Q stored in the capacitor divided by the capacitance C in farads. Okay? Now, what you see here is that a capacitor can act like a variable strength battery. When it's empty, when Q is 0, it acts like a 0-volt battery or a wire. And then the more charge I put in that capacitor, the bigger the voltage across the capacitor. It becomes a stronger and stronger battery, if you will, without the chemistry. Okay? Well, let's look at a simple, we call it an RC circuit, R for resistance and C for capacitance. And in this case, we have a single bulb and a single capacitor. Now, in the olden days when I was alive, capacitors, we weren't able to store very much charge. And typically a capacitor was measured in picofarads or microfarads, 10 to the minus 9 farads. Something like a half a farad hasn't been possible until your lifetime, when we've had some some interesting technology take place. So here I have one of those high capacitance capacitors. Here's my single bulb, and you see that it's not right now a circuit. There's a gap right here. I haven't connected this positive terminal to this lead to the positive terminal of the battery. And so this gap right here is playing the part of this open switch right there. Okay? Now, we start with the capacitor empty. If the capacitor is empty, that means the voltage across the capacitor is 0, and that capacitor is going to initially act like a wire. Well, let's look at what happens as we close the switch here. Now, initially I have 0 volts across that capacitor. We just talked about that. What about that bulb? Well, that bulb is dark, and a dark bulb has 0 volts across it. Well, any path from one side of the battery to the other has to have a 12-volt drop if there's a 12-volt battery in there. And that means the 12 volts has to drop across that open switch. And indeed, if we were to take a voltmeter and measure it from this point to this point, we would find a 12-volt difference there. Now, what if we close that switch? Well, we know that a closed switch has 0 volts across it. That's just like a wire. And we know that that battery, I'm sorry, let me do that again. We know that right after we close that switch, the capacitor is still empty. It takes time to fill up a capacitor with charge, okay? So right after I close the switch, that's still a 0-volt battery. That's still acting like a wire. And that means that all of the 12-volt drop has to be across that bulb. And suddenly that bulb is acting as if it's in a single bulb circuit, because essentially it is. The capacitor is acting like a wire. And so that means I have a bright bulb, 12 volts bright, and more flow, more glow. That means there's a lot of flow, conventional current, going through that bulb. Now, in going through the bulb, it charges up the capacitor. We end up with positive charge on this plate, negative charge on that plate. Okay? Now we know that what's really happening is electrons are going the other way. Electrons leave this plate, leaving naked protons behind, and come around and land on this plate. But we always talk about conventional current, the flow of positive charge, undoing the mistake that Brother Ben Franklin made. Okay? Now, if I wait long enough for that capacitor to get charged up, to get enough charge on it to have 4 volts across the plates, then that means there's only 8 volts across the bulb. That means it's not as bright as it used to be. And that means there's not as much flow going through it, which means not as much flow going to the capacitor. Now, there's still flow going to the capacitor, and the capacitor is still getting charged up, which means the voltage across the capacitor is still increasing. If we wait long enough for that capacitor to have 8 volts across it, now there's only 4 volts across the bulb, and it's dim. And that means there's not much flow going through it. Eventually, we get that capacitor so charged up that it now has all of the voltage across that loop. And that means that there's nothing left for the bulb. The bulb goes out. Okay? Now, let's demonstrate that. I'm going to close this switch and watch what happens to the bulb. It starts out 12 volts bright, then it gets dimmer and dimmer and dimmer, and eventually goes out. Now, you've seen that before. This is not something that you had to come to a physics class to see. You saw that when you last got in your car, if it's a newer model, and closed the door. The headlamp just went on so that you could see where your keys were, and then it dimmed out. Any analog circuit that has a dimmer like that, a timing switch, involves a capacitor. Okay? That's how we make it happen. Now, once it's gone out and the capacitor is charged up, we open the switch. And if we open the switch like that, now, what's the voltage across that switch? Well, I've got a 12 volt rise here. I've got a 0 volt drop there. I've got a 12 volt drop there. I got just as much rise as I have drop. So I don't need anything across that gap. And indeed, that's what I would measure if I measured across that gap. But what if I were to remove the battery? What if I were to take the battery out of the circuit? Well, now, I got 12 volts from here to here, a 12 volt drop. Or, thinking of it another way, I've got a 12 volt rise from there to there. Okay? Now, this is now acting like a battery, and around any loop from one side of the battery to the other, I've got to have a voltage drop equal to the battery. And that means that right now, I've got 12 volts across that gap. And indeed, that's what I would measure from here to here. But if I close that switch, a closed switch always has 0 volts across it. It acts like a wire. And so now the 12 volt drop is going to be across that bulb. Okay? And that means the bulb is going to be bright. And that means there's current flowing through it. Now remember, we're talking about conventional current, or the flow of positive charge. All of this positive charge was built up on this plate of the capacitor, and that's going to try to drive current counterclockwise. Now, in driving that current through the bulb, we're also discharging the capacitor. Charge is leaving the plates. Okay? And that means that eventually I'm going to get that capacitor voltage down to 8 volts. It's acting now like an 8 volt battery. Well, that's driving less current through the bulb. The bulb is going to be dimmer. But I'm still driving current around the circuit. I'm still discharging the capacitor. Eventually I get down to 4 volts and then down to 0 volts. And in the process, the bulb dims and the capacitor discharges. Well, let's see that. Let's watch that happen. Again, I'll dim the lights. I'm going to close the switch just by connecting these two leads. There's your 12 volt bulb, and now it's 8 volts, and now it's 4 volts, and now it's 0 volts. Physics works. That's what makes it different from biology. Okay.